Hi guys, so today I'm going to talk about heat. So last time um, we were discussing temperature, and I just want to give you another example of Vince's law that is used in medicine. So that comes from your book, okay, the textbook Johnson and Cutnell. And at the end of the chapter, they talk about thermography. So remember how we talked about black body, like the sun is burning fuel, so it's going to emit radiation, and the peak wavelength of the radiation will be inversely proportional to the temperature. So if you have the peak wavelength, you can find the temperature. Okay. So for the sun, the peak wavelength was in the green. It's a green wavelength, which means the sun is mostly emitting green photons. Likewise, we are like a black body because we have a metabolism and we are burning fuel. So we are emitting radiation and we are emitting in the infrared. Okay. So our body temperature is, if we are healthy, 37 degrees Celsius or 310 Kelvin. And if you use Vince's law, you will find that the peak wavelength for the human body, it's going to be will be in the infrared about 10,000 nanometer. Okay, so I don't know if you remember, I don't have my tablet, but you use Vince's law. Now we can use that to detect infection or places where the temperature is abnormal. Maybe it's too hot or too cool. So, for example, here you have someone, God forbid, with a breast cancer, and you look at this person with a special sensor that the sensor is able to detect infrared. And you see that in this area, that means that the wavelength is shorter than expected. So it means the temperature is larger. And you can find the temperature, and this is because there is a cancer here. On this side, there is no cancer, so this is mostly fat, so the temperature will be cooler. Of course, here the temperature is hot because, we have a lot of blood vessels, especially on the head. That's why you need to wear a hat. So that's one way you can use Vince's law and the relationship between the peak wavelength and the temperature in the medical field. So in this book that I really like, so I recommend that you get it. They also give this example here. So this is a hand, forehand before the person smokes, and this is after. And you see that the what caused the decrease is in temperature is that the nicotine that you have in smoke, when you are smoking, you get nicotine in your blood, and that will restrict the blood vessel, so there will be less radiation emitted. Okay. Here is another example. You can see that there is an increase in temperature. So again, you are using infrared sensors, maybe attached to a satellite, and this is because you have El Nino here. So this book that I recommend is really nice because it has solved problem and also very nice examples. So let's go back to heat and let's go over some history. So in the 1800, so at the end of 1800, you had this very famous scientist. He was French. His name is Antoine Lavoisier. And I'm sure you know him because he famously said that nothing can be created, nothing can be destroyed, everything is transformed. So he's the one who came up with conservation of matter. And for example, he is the one who explained combustion when oxygen, you know, will make combustion possible. And you can Google all what he did. He also explained rust. Okay, so people at the time thought rust will pop out of nowhere, and he explained that no, rust comes from the reaction between iron and oxygen. So at the time, if you wanted to do experiments, okay, you had to pay for it, okay? It's not like today you can work for a university that will pay for your materials, the materials that you need to do the experiment. So he was a tax collector for the king, Louis the 16th, and he used his money to make all those experiments. So he's really the father of modern chemistry. Okay, so I'm just giving you a little bit of history there. His wife here is Marie Lavoisier, and she was also very famous because she was the public voice of Lavoisier, who was very shy, and she's the one who was drawing all the experiment that he was doing. Okay, so she took drawing lesson just to draw his experiments, and he was very recognized in the academic of science in France, right? So he did all these experiments. He was really the first one to carefully, meticulously do all those experiments. Unfortunately, he lost his head in 1794. I think he was only 50 years old because it was the French Revolution. And first of all, he was a tax collector for the king, so that was not a good thing, I guess, at the time. But also, he upset um, another character very famous in France. His name was Marat. So he was a failed scientist because when Lavoisier was at the French Academy, he went to show Lavoisier his work, who dismissed him. He said, no, what you are doing, the work that you did online doesn't make sense. So he got very upset and he took his revenge. So after the French Revolution, so they cut the head of the king and the queens and many other people. It was very bloody at the time. He became to work for the people who did the revolution, who took over the king. And what he was doing at the time is to collect all the names of the people who betrayed the revolution, right? So he sent Lavoisier to the guillotine. So he's the one, because of revenge, who sent Lavoisier to the guillotine. And someone, a British guy, forgot his name, with a lot of humor, said it's British humor, said that it took 100 years to grow such a head, but it took like half of a second to lose it, because of course he was a genius, right? And another interesting story. So this guy, Marat, had a skin disease, like I think it was psoriasis, like a skin condition. So all his day he was in a bath, and he was killed by a woman named, I don't know if you can see her here, Charlotte. I think her name is Charlotte. So his name was Jean-Paul Marat, and he was killed by Charlotte Corday, who took revenge for all the people that he killed. Unfortunately, she also lost her head um, with the guillotine. So anyway, so Lavoisier was really the father of modern physics, modern chemistry, but it didn't have the right idea about heat. Almost there, but not quite. He thought that heat was some kind of weightless fluid named caloric, and that fluid will flow from hot object to cool object, but that fluid will be in limited amount in the hot object. So for example, if you have a candle burning, that liquid was inside the candle, and when you burn the candle, that liquid will flow, invisible liquid will flow in the air, and then the candle stop burning because it will run out of that liquid. Okay, so that was called the caloric theory, which is not the right idea, of course, but it's not far from the idea because obviously something is flowing from hot cold, but it's not a fluid. Okay, we're gonna see it's energy flowing. So then came Benjamin Thompson, okay, who was Count Rumford, and also very interesting history. So at some point he ended up in uh, Munich, so in Germany, what is today Germany, and he was boring cannons for the German army at some point in his life. Okay. And he understood that as long as he was boring, the cannon will get hot. And then he stopped boring the cannon and the cannon will cool down. So it means you could not have that fluid because in limited amount. So he understood that heat was actually what was happening is that mechanical work will turn into thermal energy. Okay, so he understood that heat was not a fluid. Okay, heat comes because you have energy transformation from mechanical work to thermal energy. So he was able to prove Lavoisier wrong. But so that was the first step toward understanding what heat was. So what's interesting about this character is that so Benjamin Thompson was actually American, and but he was spying for the British. So during the American Revolution that I think cost the King of France his head because France helped the American a lot with a lot of money. They didn't get back the money, and that was really bad for the finance of the French um, of France, by the way. So anyway, Benjamin Thompson had to flee the US, went to England, and he didn't get along with the British either, so he went to France. In France, believe it or not, he married um, the widow of Antoine Lavoisier, whose head was cut, Marie Lavoisier, but their wedding didn't last long. So it's interesting that he married the widow of Antoine Lavoisier, who he proved wrong. And then he went to Germany, and he also made many inventions, like the Rumford oven. If you can. So he has a very interesting story. So I don't know if we can find his invention. I think it's called the Rumford oven. So it's interesting. If you are an engineer, you want to dig more into that. It's a type of oven that is more efficient. So improve those ovens at the time. Okay, so that was for Lord Rumford. Okay, so his idea was later developed by James Prescott Joule. So Joule is the unit of energy that we are using today. And Joule in 1850 did that set of experiments that are very famous that show that energy is can be transformed from one form to another. So for example, here you have a weight above the ground, so it has potential energy. Okay, so you let the weight fall. So that potential energy is going to turn into mechanical energy. So rotational kinetic energy, okay, because it's going to spin. And because of the friction, that's going to go into heat. And the temperature will turn into thermal energy, and the temperature will rise. And he was able to quantify, okay, the amount of thermal energy. Okay, so he was able to quantify to show that the change in temperature was proportional to the work done by gravity on the mass. So it's the first law of thermodynamics. It's a conservation of energy. So you go from potential energy to kinetic energy, and then you're going to get heat, and you're going to get thermal energy. Okay. So I don't know if you can, if I have like, here is the experiment. So you see the thermometer here is there. I don't know, I guess it's 18 degrees Celsius. So about, I don't know, 67 Fahrenheit, something like this. So this is falling. Okay, so it has potential energy. That potential energy turned into rotational kinetic energy that will produce heat, and the thermal energy here is going to increase. That will lead to a rise in temperature. So temperature here is 17.5, and it's going to increase here. So all that uh, potential energy is going to turn into thermal energy, and you can see the increase in temperature. So this is a very famous experiment. So he was able to quantify thermal energy. So he was able to show that it takes 4 joule, okay, or 1 calorie to increase the temperature of 1 gram of water by 1 degree. Okay, it's about 4 joule, or the one that we are using in the food. You know, when you read you know, how much calorie there is in food is actually kilocalorie. So it's 1,000 calorie. So it's an uppercase calorie. So he was able to quantify that it takes 4,000 joule to increase the temperature by 1 degree of 1 kilogram of water. So he was able to show that heat is actually energy in transit. Heat is energy being transferred. Okay, so the same way that work in physics, okay, it's energy in transfer. Heat is energy in transfer that happens because of a result of a difference in temperature. So if you take a hot object and cool object, heat will flow from the hot object to the cool object. So it's not really a fluid, it's energy in transfer, but Lavoisier was not too far from the truth. Okay, so here you have a link, and you can dig into that experiment that Joule did. So you see here that website here. They talk about Count Rumford. So here he was working for the army in what is now Germany. And you see, so he proved the caloric theory wrong. There is no such thing as a weightless fluid flowing. And he wrote a book about that. So there was a relationship between heat and mechanical work, right? So you can turn mechanical work into thermal energy. And that was further developed by Joule in 1843, which is the first law of thermodynamics. So I recommend to go on that website here, or you can take a screenshot, but it's better to go on the website itself. Okay, so let's go back to the definition of temperature. Temperature is the kinetic energy per particle. Okay, and not any kind of kinetic energy, is the translational. So it's the average translational kinetic energy per molecule. So if you have a gas here, the molecules are going to move in a random fashion in all directions. And if they all have the same mass here and there, you see this one have larger speed. Okay, so the kinetic energy will be proportional to their speed square. Lower speed means lower temperature. So they are always moving in all directions. Okay, now what we call thermal energy, that means it depends on the density. So it means you need to find the total amount of kinetic energy. Okay, whereas temperature is the average kinetic energy per particle. So, for example, here you have an oven, 400 Fahrenheit, and here you have boiling water, 212 Fahrenheit. And if you were asked, where is it that you can put your hand in, okay? If you have the choice, of course you will say the oven, right? And not the boiling water. Even though the temperature is larger, even though the kinetic energy per molecule is larger, because the density is smaller, the thermal energy will be smaller. So it means if you put your hand, of course, some molecule will hit your hand, but not many. If you put your hand in the boiling water, you have all those molecules hitting this hand. So, of course, the molecules of your hand wants to join the party. The molecule of your hand in your skin will start to jiggle as well, okay, because the motion will be transferred. And, of course, that will destroy your skin. So that's how it works. So, for example, here you have sparkler sticks. And they do have a very high temperature, but you cannot warm up a room with this, okay? You cannot use that as a heater because there won't be enough thermal energy. So the total amount of thermal energy will be low, even though the temperature will be large. So heat is energy that is being transferred from hot to cold, and if heat doesn't not have time, okay, to flow, of course your feet here will not be burned, okay, because the heat does not have time to flow in large amount because you don't stay in place, you keep moving. Plus air is not a good conductor, so there is a layer of air between air and also water if you are sweating, so that will protect your feet. So heat is really energy flowing, and if that energy cannot flow well, okay, because it does not have time to flow, or there is some insulation between the two bodies, so you're not going to feel the burn. Okay, so heat is a transfer of energy from hot to cold. So something is flowing, but it's not a fluid. Okay, so it depends what is it in like if you have a metal bar here, of course the flow will be easier than if you have vapor between the hot body and the cool body, right? but the idea is that heat is energy flowing, okay? Energy in transfer, energy in transit. And the unit for heat is Joule. The same way that work is energy is in transfer as well. So I'm doing work on something, that means energy is being transferred. So it's the same idea. But you see that Lavoisier was not very far from he had the idea right? Something is flowing, but it's not a fluid, it's energy flowing. Okay, so that will be the definition of heat. So you need a difference in temperature for heat to flow. So you might ask, so that's the definition of heat. So heat is energy in transfer, in transit from a hot substance to a cool substance, or from a hot substance to a cool substance. The substance here is at 37 degrees Celsius, and maybe that cool substance could be at 0 degrees Celsius, so heat will flow, but it's energy. The unit for heat in SI unit is the Joule. So just a parenthesis here. So you cannot say that a substance contains heat. Okay, so it's not like a caloric fluid. It's not a fluid, but it's just energy being transferred because of a difference in temperature. So for example, just a parenthesis, if you have two objects, one is made of wood, for example, one is a metallic object, and they are in the same room. So at some point they will have the same temperature as the room. So that will be the zero law of thermodynamics. After a while, they will reach the same temperature. Now, if you touch it, you are at 37 degrees Celsius, right? So heat will flow from you to the spoon. So this one or to that one. But this one, because it's made of metal, will feel cooler. It's not because it has a lower temperature than this one. It's just because metal is a better conductor, so heat will flow faster. Okay, so we'll talk about that later. But it's when you talk. It's when you walk on fire here or burning coal. There is a layer here of vapor and sweat and air, so it's not a good conductor, so heat cannot flow really fast. Okay, it's just a parenthesis. It also depends how fast the heat it's going to flow, depends on the conductivity as well. Okay, so let's go back to heat. So unit is Joule, and for Joule, so you need 4 joules to increase 1 gram of water by 1 degree Celsius. And 4 joule is the same as 1 calorie. Okay, so that's another unit for energy that they use most in chemistry. So when they say the food calorie, okay, it's not the same calorie, it will be 1000 calorie. So if you see a cookie, chocolate cookie, and it says 100 calories, it really means 100 kilocalories. So a cookie with 100 calories means that it has 1000 lowercase calorie, which is 4000 joules. So it's a lot of energy in a cookie, 4000 joules. Another unit is the BTU that is used in the US. So that will be the amount of energy that you need to bring to 1 pound of water to increase its temperature by 1 Fahrenheit. So it's a different unit. Okay, so we can have this relationship here. So Q is the amount of heat that needs to be flowing to a substance of mass m, so that will be the mass in kilogram, to increase or to change the temperature by delta T. And of course, it depends on the substance. So this is called a specific heat capacity. So that will mean the amount of heat that you need to increase the temperature by 1 degree Celsius for 1 kilogram of the substance. Okay? And not all the substance can react the same way. So, for example, water has more inertia. It means it resists the change in temperature. But anyway, we're going to get to that. But you see the specific heat capacity, the unit is Joule per kilogram Celsius. Okay, so the amount of energy necessary to increase 1 kilogram of substance, to increase the temperature of 1 kilogram of substance by 1 degree Celsius. So here you have the heat capacity, the specific heat capacity for different substances. And you see here that water, okay, you need 4,000 joules, okay, to change the temperature of water by 1 degree Celsius or by 1 Kelvin, because the difference in 1 Kelvin is the same thing as the difference in 1 degree Celsius for 1 kilogram of water, okay, which is about 2 pounds. Okay, so 4,000 joule is about 1,000 calories, or one kilocalorie, or 1 food calorie. Okay, so 4,000 joules is 1,000 lowercase calories. So it means it takes a lot of energy to change the temperature of water by a tiny bit. So we can say that water has a lot of inertia, thermal inertia. So it's resisting the change in temperature. So it means also that water can contain a lot of thermal energy. Okay. And then when it contains that thermal energy, it takes a lot of time to release that energy. So, for example, for a given mass, if it takes 20 minutes to bring water to a boiling temperature, it will take 2 minutes for iron and 1 minute for silver. Aluminium, for example, if you compare those two numbers here, you see that aluminium, it takes only 100 joules to increase the temperature by 1 degree Celsius for 1 kilogram of aluminium. And you know that if you have a pan, for example, on the stove, very quickly, when you heat it up, very quickly you're going to burn your finger by touching it, right? But when you are boiling water, it takes forever to boil water. You can stick your finger in the water. It takes a long time to reach the 100 Celsius temperature. So 4,000 joules is the same as 1,000 calories, or 1 kilocalories, which is the same as 1 food calories. So here you have the unit in calorie, but it's in grams. So it takes 1 calorie to increase 1 gram of water by 1 degree Celsius. So that comes from your textbook. The unit is joule per kilogram Celsius. But water is here, so still 4,000 joules. Okay? So water has a very large specific heat capacity, which is very good for human, okay, for life to thrive on Earth. So again, 1 gram of water requires 1 calorie of energy to raise the temperature 1 degree Celsius. If you compare that to iron, if you compare the two numbers, right, 904,000. So if you compare that number to this number, you see that the ratio is about 1/8. So if you want to change the temperature by the same amount, you will need 1/8 as much as energy for iron, okay, for the same mass. So water has a very large specific heat. Okay? So water is able to store a lot of energy, thermal energy and other kinds of energy. So here is interesting. So that slide comes from the textbook Conceptual Physics by Paul Hewitt that I also recommend for this class. It's a conceptual book, but it's also very interesting. So you see here, Europe, France is here, and New York City is somewhere over there. And New York City is very cold during the winter and very hot during the summer. Can be even hotter than in Florida and very humid too. So New York City or New York has extreme temperature, but for the same latitude here, so if you go to France, it's not as extreme. It's not very cold during the winter. Like if you go to Paris here, it's not very hot during the summer. And why is that? It's because you have like a flow going a flow of water, the Gulf Stream. So the Gulf Stream here goes from the Caribbean to Europe. So because water has a capacity to hold all that thermal energy, that energy here is going to be transferred here to Europe, warming up Europe, right? So it's not going to be as cold as here because water has a capacity to hold a lot of energy. So that will explain why Europe is not as extreme as New York. If you go upstate New York, it's extremely cold. You know, if you know Ithaca, for example, it's north of New York, extremely cold. So if you like cold, you know, it's fine. Okay, so if you have countries by the ocean, it's not going to be as cool as inland or as cold as inland because the water will mitigate the temperature because water has a capacity to hold heat or to release. It will take a lot of time for water to increase its temperature, and it takes a lot of time for water to decrease its temperature. So if it's very hot during the summer, so the water will still be cool and it takes a long time to warm. Okay. And if it's very cool in the winter, it takes a lot of time for the water to cool down. Okay. Whereas the ground and the dirt does not take as much time. Okay. So, for example, here in the US, you have the wind flowing toward the west. Okay, so if you have California, the weather is always great because the wind comes from the ocean, and the ocean does not decrease its temperature much during the winter and doesn't increase its temperature much during the summer. But if you look at those eastern cities here, like New York City, or New York, all those states here by the Atlantic Ocean, the temperature will be more extreme because the wind goes from the land to the west and the land has a lower specific heat. So in winter, it's going to be very cool and the cool will be brought westward. And during the summer, it absorbs heat quicker. So you're going to have warm wind flowing in this direction. Okay. So it takes a lot of time for water to cool down and it takes a lot of time for water to warm up. which keep the people by the water very happy if you live here, for example, or if you live there. So I hope this was clear. So let's start doing some math now. So you can pause the video and try to answer this question. So that comes from the book Johnson and Cutnell. Okay, so let's do this very simple problem here. And so human body is about 80% water. So the specific heat capacity is close to 4,000. It's about 3,500 joule per kilogram degree Celsius. And the mass of the jogger is 65 kilogram. And Q produced by the effort is 8 times 10 to the fifth joule. Okay, so let's see the increase in temperature. If that amount of heat is produced in half an hour, and if the human body didn't have a self-regulating temperature regulating system. Okay, so let's apply the equation. Q equals mc delta T. So you can pause the video. So 8 times 10 to the 5. So that will be the energy produced. And M produced by the machine here. So the mass is 65 times 3,500 times delta T. Okay, so you can do the math. You can get your TI. You see here you have 8 times 10 to the 5. Enter, divide by 65 times 3,500. Okay, the increase in temperature is 3.5 degrees Celsius. So that means if we didn't have this temperature regulating system, because of the effort, the temperature of the body will increase from 37 to 40.5. So that will be very bad, because if you keep producing energy, if you keep exercising, the temperature will keep increasing, which is not a good thing. So luckily our system is very nicely working. Okay. Here is a question more for engineers. It's more technical. So you have a failure, and maybe you lose power, and it's very cold outside. So maybe it's in New York, for example. Oh, it's very cold, 5 degrees Celsius, and now the power is working again, and you want to increase the temperature to 20 degrees Celsius. So that will be the rate at which energy is produced by your heating system. So that means 30,000 joule per second. And that will be the heat capacity. So it's not specific heat. Specific heat depends on material like aluminum, iron, water. So heat capacity depends on the object. Okay, so this is found by trial and error, right? So if you go back to here, this heat lowercase c is a property of a material. Okay, so it's called a specific heat. But if you have just uppercase here, the mass is included inside. So it depends on the property of the object, and this is called the heat capacity. So not to be confused. But anyway, you don't need that definition, because you see what it means. You see the meaning just by looking at the unit. So it means you need 25 megajoule to increase the temperature of the house by 1 degree Celsius. So very often in physics, you just look at the unit and it gives you an idea of the meaning, okay, of that physical quantity. Okay, so you can stop the video and try to solve this problem. It's not very hard. You can go step by step. So first of all, you want to increase the temperature from 5 degrees Celsius to 20 degrees Celsius. So that means that the increase uh, in temperature that you want to achieve, it's going to be 15 degrees Celsius. Okay? And then um, you see that 25 megajoule, okay? Because of that house, specifically in this house, you need 25 megajoules to increase the temperature by 1 degree Celsius. So if you want an increase of 15 degrees Celsius, so how much energy you need to provide? So you just multiply, right? So it's going to be 25 times 15 times 10 to the 6 joule, which is, if you do the math, it's going to be 3.75 times 10 to the 8 joules. You can round to 3.8 if you have two significant value. Okay, you can make sure that I did it right. So 25 times 15 times 10 to the 6 here. Scientific notation, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 3.8 times 10 to the 8 joules. Okay, and the heating system, so that's what you need. That will be provided, okay, by the heating system. So the heating system in the house, okay, it's going to produce energy at a rate of 30,000 joule per second. Okay, because watt is a unit of energy. It's really it's a unit for power. Okay, and it's really joules per second. So it means energy divided by the time. That will be power. So it means that the heating system can produce 30,000 joules in 1 second. And we want to produce 3.75 times 10 to the 8 joules. That's going to be question mark. So you're going to divide, okay? So you cross multiply, divide. So you divide this by 30,000. So 1, 2, 3. Okay? So the time, it's going to be 12,500 seconds. Okay, so you can divide by 3,600 and you get about 3.5 hours. Okay, I keep 2 digit because I had 2 digit here and there to begin with. So 3.5 hours. Okay, so that could be you can go to a cafe, for example, waiting for 3.5 hours because 5 degrees Celsius is really cold. Really cold. Okay, so here is another question. So those questions come from a textbook called, I think it's called Fundamental of physics that I also use. And the author is Wolfson. Okay, so just if you are interested. So let's do this one. Okay, it's the same kind of problem, I think. So you can pause the video. So burner, okay, so it means you have a stove here. You have a flame, so it's using gas, and here you have water. You have 2 kilograms, which is about 2 liters or 2 quarts. So you're gonna have heat, so it means energy flowing from hot to cooler. That will be Q. And we suppose that no heat is lost. So it's like you can neglect the loss of heat around to the surrounding. Okay, so Q. Okay, so it's gonna be the mass of water times the specific heat times delta T. And we know that the mass of water is going to be 2 kilograms. Delta T, it's going to be from 10 to boiling. The boiling point is 100. So that's going to be 90 degrees Celsius. Specific here heat is going to be 184 joules per degree Celsius and kilogram. Okay, so we can find Q. We're going to find Q. So it's going to be 2 times 4, 184. Times 90. So that's going to be, if you do the computation, that's going to be, I think it's going to be 7.5 times 10 to the 6 joule. But let's make sure that's the correct answer. So it's 2 times 4, 184 times 90. So 7.5, 1, 2, 3, 4, 5. It's a 5. It's a 5. Okay? 7.5 times 10 to the 5. 90 degrees. And here you have 2 kilograms. Okay. And then it's the same thing here. The burner, the rate at which energy is produced here is 1500 joules for 1 second. So if you want 7.5 times 10 to the 5, then it's going to be, so you cross multiply divide. So you divide by 1500. Okay, so you get 502 seconds. So let's divide by 60. So it's about 8.4 minutes. And I keep two digits. Okay, so that's not bad. I just wanted to go back to this problem. I forgot to point out something here. You see that the energy produced because of the effort was 8 times 10 to the 5 joules, right? And remember that 4 4,000 joules. So it's a little bit more, but let's simplify here. So 4,004 joules is the same thing as 1 uppercase calorie, which is 1 kilo lowercase calorie, which is of course 1,000 small calories here. So this is used in chemistry. This is the food calorie. Okay. So 4,000 joule is one food calorie, which is 1 kilocalorie. Okay. So it means you have a lot of energy in food. So it means here, so if I want to find out how many calories is being used in the problem, then you're gonna have you divide, so 8 times 10 to the 5 divided by 4,000. So you have about 190. Okay, so 190 food calories. So it means that if we didn't have the temperature regulating system that we have, okay, then that means you eat a chocolate cookie here that has about 190 calories, and your temperature will rise by 3.5 degrees Celsius, which will not be very cold. Okay, so let's do another one. So this one is also very interesting. So you have, so it means when two body comes together, they're gonna reach the same temperature. Okay, once they are at thermal equilibrium, one is losing energy, losing heat. The other one is gaining energy. Okay, so heat that is lost, it's gonna be negative. Heat that is gained is gonna be positive. Okay, so if you have two body, okay, in contact, so this one is hot and this one is cold relative to that one. So heat will flow from the hot to the cold. We suppose that the system is insulated. Okay, so you have conservation of energy, which is the first law of thermodynamics. So it means the energy lost by one is gained by the other one. Okay, so it means in that case, it should be actually that should be one and that should be two, because two is gaining energy, so Q is positive, and one, the system one, so that will be system one and that will be system two. So this one is gaining energy and this one is losing energy. Okay, so this is conservation of energy, which means that Q1 plus Q2 equals 0. So this one is negative and this one is positive. So with these kinds of problem, you have different way to do it. Now, if you take the absolute value, so you want to make sure that Q1, you take the absolute value of Q1, so it's going to be positive. So then it's going to be equals to the absolute value of Q2. Otherwise, you can say Q1 equals minus Q2. Okay? So what's happening here? You have two systems, so two objects. You have iron. So you have a piece of iron here. Okay, so that will be system 1. So iron, I'm going to put iron here. And you have the mass. You have the mass of iron is 1.2 kilogram. And the temperature T1, initial temperature is 650 degrees Celsius. And you have the specific heat for iron, which is 900. I think it's 900. No, it's not. It's 650. No, it's not 650. Let's find out. It's how much is iron? Iron, 447. So 447 Joule. So it takes 447 Joule to increase the temperature of 1 kilogram by 1 degree Celsius. So that will be for iron. Okay. And system number 2, it's going to be water. Okay. So for water, we have a mass of 23 kilogram, and we have a temperature of 20 degrees Celsius, and the specific heat is 4184 joule per kilogram degree Celsius. So what's going to happen here? Heat is going to flow from iron to water. And it takes a lot of heat to change the temperature of water. Okay, so that means water has a lot of inertia. It resists the change in temperature. So you're going to see that surprisingly, water, it doesn't seem to change its temperature by much, but iron has a very low inertia, thermal inertia. So its temperature is going to change by a lot. So you have different way to do this problem. After, I'm going to show you one way and then you can do the other way. I'm just playing. Okay, so you can pause the video. Okay, so you can say that Q2 equals minus Q1. That will be one way to do it. So Q1, okay, so Q1, 1 is iron, okay? So iron is losing. So we can say that C of iron, so 447 times 1.2, okay, times 447 times 1.2 times the final temperature minus initial, which is 650, okay, will be equals to, I put a minus here, okay, so that becomes positive. So minus Q1 equals Q2. So that's going to be 4184 times the mass is 23 times final temperature minus initial is 20. Okay? So then you need to do the math. And I don't have much space to do the math, but it's just algebra. Okay, so you can distribute here, distribute there, distribute here, distribute there. So if I distribute, I'm gonna get 348 660 minus, so that will be this multiplied by that, minus 536.40 equals 96,232T minus 192,4640. and you keep going, you isolate T. Okay, I don't have space, but it's not so hard. And the answer will be 23, I think I found 23.5 degrees Celsius. That's going to be the final temperature. So you see that the water didn't increase its temperature by much, only 3 degrees uh, Celsius, 3.5, but the iron lost a lot of temperature, right? It went from 650 to 23. So it means that water has a very large thermal inertia. It's very hard. You need to feed water a lot of heat to change its temperature. Okay? And you see, even though the mass of the water was 23 kilograms and the mass of the iron was 1.2 kilograms. So a different way you could have done it. You could have done all the algebra first, isolate T here, the final temperature, and then you can solve for T. And you will still find 23.5 degrees Celsius. I could have done it, but it's just algebra, right? You need to distribute, and then you isolate T, and then it's just combining like terms, so it's not that hard. Okay, so this problem, so this one is also from the book Johnson and Cutnell, and that's one slide from the book, and it's an interesting problem, especially if you have to take chemistry lab. You already have done such experiment. So this is called a calorimeter, and it can be used, for example, to measure how many calories in a piece of food, for example, or it could be used to find unknown materials. So in that case, such as in that case here, so you have a cup of aluminum and you have water. Okay, and the whole thing here is insulated. So you place something very hot or something that you burn inside. So the amount of heat lost by this substance is going to be transferred. So the energy will be transferred as heat from that substance here to the water or to the aluminum cup. So I don't know if I have here. That's a small simulation. So you see, it comes from a chemistry website. So maybe this is food here. So you have combustion that will happen because there is some electric tension there. So the food will be consumed, and all that energy contained in the food will be transferred to the water. So the water will have an increase in temperature. So by finding the increase in temperature, you can find how much energy was transferred. So what it looks like something like this. You see, it's very cheap. You can buy that on Amazon or a website that sell materials for experiments. Okay, so you can pause the video, and it's not hard. It's just that they want to make sure that you know reading comprehension. Okay, so you have yeah, actually you have two material. So this is the unknown. So I'm gonna call that system 1. So that will be your unknown. Okay, so the unknown has an initial temperature of 97 degrees Celsius because it has been heated before it is dumped in the water. Okay, and then here you have system number 2. That's going to be your water, and you also have the cup system number 3. You have the aluminum. So you see that heat is going to flow from the unknown to the water. So I'm going to call that Q2. It's going to be positive. And then it's going to flow from the unknown to the aluminium. Okay, that's going to be Q3. And Q1 is the amount of energy lost by the unknown. Okay, so Q1 will be equals to Q2 plus Q3 in absolute value. So that will be a positive quantity, that will be a positive quantity, and that will be a positive quantity. Okay? So energy lost by this one equals energy gained by that one plus energy gained by that one. So it's just conservation of energy. Okay, so system number 1, it's going to be the unknown. And we see that the initial temperature is 97 degrees Celsius. And the final temperature, when everything is at thermal equilibrium, everything, aluminium, water, substance, here they all have the same temperature of 22 degrees Celsius. Okay. And then what else do we know? Maybe we know the mass. Yes, 0.04 kilogram. And we don't know the specific heat. That's what we want. So system number 1 will be the unknown. And then system number 2, it's going to be the water. So initial is 18 degrees Celsius and final is 22. So again, it's very hard to change the temperature of water. The mass of water is 0.2 kilogram. The specific heat for water is 4184 joule per kilogram degrees Celsius. And the system number 3, okay, the final initial temperature. So this is aluminium. So initial temperature is 18 degrees Celsius. The final temperature is 22 degrees Celsius. The mass of aluminium is 0.15 kilogram. And the specific heat, we have seen that before, is, I forgot, 900 joule per kilogram degree Celsius. Okay, so the energy lost by the unknown, okay, will be gained by the water and gained by the aluminium. So I'm going to hide this conservation of energy and I want to make sure that everything will be positive. So for the, I'm going to start with water. So it's going to be 0.2 times 4184. Okay, so the final is 22 minus 18 plus aluminium. Aluminium is 0.15 times 900. And here the same. Final is 22 minus 18. Okay, so this is gain. And that will be equals to the energy transfer from the unknown substance. Unknown substance has a mass of 0.04 times C1 times, so the final is 22, initial is 97. But here there should be a minus, right? Because it's what is gain equals to what is lost. So I want to make sure that this is positive, that's going to be positive. So I'm going to put here 97 minus 22. Okay, so it's easier than before. the algebra is easier because I want to solve for C1. Okay, so if I do the math, I'm going to get all that. That's going to be 540 plus this quantity here is going to be 3000, okay, equals 3 times C1. And we can solve for C1, which is in that case, okay, so it depends which value you selected for aluminium, joule per kilogram Celsius, which is about 1300 joule per kilogram Celsius. Okay, so I look it up and I'm not sure, but 1300, for example, a specific heat could be, for example, natural resin. Could be. Or it could be some kind of wood. So that could be the unknown substance. So, okay. You see, that will be the answer. And it's just, so this kind of problem you can find for the MCAT, even in chemistry. And it's just a matter of organizing the information. So first you have a nice drawing to explain what's going on, and then you can lay out the math. Okay. Let's see. I had one more problem that comes from your book here, and okay, I think it's page 360. So this one comes from your book. You see here you have cold shower, and there is a heater, and the temperature is going to rise to 61 degrees Celsius, and someone is taking a shower. Okay, so first question, find the energy needed to heat the water. So it's going to be from 15 degrees Celsius to 61 degrees Celsius. So it's going to be 60 minus 10 is 50, minus 5 is 45. So it's going to be 46 degrees Celsius, I think. Right? 60, 50, 45, 46 degrees Celsius. So the amount of energy transfer from the heater to the water, it's going to be 46 times 120 times 4, 184. And if you do the math, you're going to get 2.3 times 10 to the 7 joules. Okay. Assuming that you charge, so the utility company, so that could be in Florida because electricity is very cheap over there. That could not be New York, where electricity is like 20 cents. 10 cents is very cheap. I don't think even in Florida that it's going to be 10 cents per kilowatt hour. So kilowatt hour, watt hour is a unit for energy. So 1 kilowatt is 1,000. Hour is 3,600 seconds. So that will be in joule. Okay, so you just have to know that 1 kilowatt hour is a unit of energy, and that's going to be 3.6 times 10 to the 6 joule. Okay, because energy is power times time. So if you have energy in kilowatt hour, so it's power in kilowatt times time in hour. Okay, or joule is watt times the time has to be in seconds. So if you want joules, you're going to do 1000 times 3600. So anyway, so 3.6 times 10 to the 6 joule is going to cost you 10 cents. So here you're using 2.3 times 10 to the 7 joules, question mark. So you cross multiply and you divide, right? So it's going to be 0.1 times 2.3 times 10 to the 7 divide by 3.6 times 10 to the 6, and you get about 64 cents. Okay, so that comes from your book here. Okay, so that's it for this